Okay, let's take a look at an example of nucleophilic addition reactions with carbonyl compounds. Aldehydes and ketones undergo these reactions. So hemiacetals and acetals, what are they? Well, a hemiacetal, you look at a carbon and it has two oxygens bonded to the same carbon. Both acetals and hemiacetals have those. The difference is hemiacetal has an OH, a hydroxyl group, and an alkoxy group. So it could be like OCH3. Basically, on the other side of the oxygen is a carbon. That's an alkoxy group. An acetal has two alkoxy groups. So a hemiacetal is sort of on its way to becoming an acetal. So which of these compounds at the bottom of the screen contain hemiacetals? Well, compound A, if you look here, there is a hydroxyl group on that carbon, and then on the same carbon, a methoxy group. So it's almost like one carbon has an alcohol and also an ether type connection, COH, COC. Now, is there a carbon like that in the compound B? Yes. That carbon has two oxygens. One is an OH, a hydroxyl, and one is an ether type linkage, an alkoxy group. So that is yes and yes. Now, there is no hemiacetal in this compound. This carbon has an OH, it doesn't have any other, so it has an alcohol. And then this oxygen has a carbon on both sides, that's an ether functional group. This last example does have a carbon that is a part of a hemiacetal. Has two oxygens on the same carbon. One is a hydroxyl and one is an ether style linkage, an alkoxy group attached. So that is yes. So here we see how you form a hemiacetal. You start with an aldehyde or ketone and an alcohol, and you need an acid catalyst. Usually you just go to a hemiacetal. In some cases you can push it and get an acetal. One alcohol molecule has added into the carbonyl carbon to make a hemiacetal. Two molecules of the alcohol have added to make an acetal. So the general mechanism is that you protonate the carbonyl. So you activate the carbonyl, and then the nucleophile, the alcohol as the nucleophile attacks. These electrons move up to here. Of course, that's positive to start. And then, of course, you lose H+. H+ was added as a catalyst. It protonated the carbonyl, and then it comes off at the end. So, can we predict the hemiacetal that we would form here? Well, we know that this oxygen is going to attack here, and these are going to go up. And this is going to become an OH. We're going to protonate with the catalyst. That will become an alcohol type group on that carbon, and then this hydrogen will come off in the end. We'll lose it because H+ is a catalyst. So basically, you look at the carbon chain. So you look at the carbon chain. that carbonyl carbon is going to become OH. And then bonded to that will be the oxygen from the alcohol without that hydrogen. That hydrogen comes off during the mechanism. So let's take a look at that mechanism. We're going to have a catalyst, an acid catalyst. This will get protonated. And then our alcohol will attack this. Okay. This still has the hydrogen on it. So now that's the plus charge on that oxygen there. And then we're going to lose this hydrogen. We can show this hydrogen still there. It's implicit, you don't need to show it. But the hydrogen ion was a reactant, and then later it was reproduced as a product, so it's a catalyst. Now, how do you reverse this? It's called hydrolysis. So when you want to go this way, you have alcohol probably as your solvent and a little acid catalyst. That'll push the equilibrium to the right. But if you want to go backwards, water is the solvent. And so the equilibrium will go in the reverse direction. And the way this works, I'll just make that a methyl group to be easy. If you have an acid catalyst, you might protonate that oxygen. Okay. And then this will return to its carbonyl and kick this off. Okay. And then regenerate H+. Because that was a catalyst. So to do a hydrolysis, you use, you take your hemiacetal, add lots of water, acid catalyst, and you shift the equilibrium back. So how can you look at a hemiacetal and tell what it was made from? Well, you look for the carbon that is a hemiacetal carbon. That's the one that has the OH and the alkoxy group, a methoxy group in this place, in this case. So what you're going to do is say, this carbon, this will become the carbonyl. This bond will break, and this becomes the alcohol. The alkoxy group is the alcohol. So if you were to do hydrolysis of this, the long carbon chain, that oxygen reverts back to the carbonyl, and our alcohol is the carbon chain that's on the oxygen that's bonded to the hemiacetal carbon that becomes the alcohol. So writing this reaction is the same as answering the question, what is the alcohol and what is the carbonyl compound from which this was made? If you can identify the two parts, you can write the equation. So here's one that's a little tricky. Kind of looks like what we see in carbohydrates. It's a cyclic case. That's our hemiacetal. You see we have two oxygens. One is an OH and one's an alkoxy group. The oxygen in the ring on the other side is a carbon and a hydrogen. So just because it's a ring, an intramolecular hemiacetal, doesn't really make it any different. We're going to consider what was the carbonyl. Well, the OH was formerly the carbonyl. The other oxygen added in from the alcohol. So this came from the alcohol. So if you start with let's take this as the hemiacetal carbon, right? What is on that? Well, the OH is the carbonyl. Here's our CH3. I'll draw it just to make it clear. And then, so that's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And what's on carbon 6? An OH. Okay. So how do you make that? Usually it's an alcohol plus a ketone or aldehyde and acid catalyst. But in this case it's one molecule. Both the alcohol and the ketone are in the same molecule. That's how you make that. I won't go into the details here, but I've shown you how a hemiacetal can produce an acetal. What's interesting, I will just point out this. If you look at this acetal at the bottom, there are two alkoxy groups. So if you say to yourself, what was that made from? Think of those two oxygens merging into one. That's the carbonyl. That carbon right there was the carbonyl, and there were two alcohols, CH3, two of those that added in. That's, if you follow the mechanism, you'll see first one, you get the hemiacetal, and then you make the acetal by adding a second one. And so we talked about this with carbohydrates. When you look at the cyclic form of a carbohydrate, you see what's called the anomeric carbon, where that OH, in the open chain form, that OH is the aldehyde or ketone. Since it's glucose, it's the aldehyde carbon. And one of the oxygens that was an OH reacted in this fashion with the carbonyl carbon and formed a ring. So you see down here, this is the open chain form, and if you protonate this oxygen, that makes it a better electrophile, and this oxygen will then attack that carbonyl carbon, and the OH of the hemiacetal can be up or down, and that's where we get alpha and beta. Now if you make a disaccharide like cellulose or starch, those are polymers actually. It's the same for disaccharides or polysaccharides, but when you join two carbohydrates together like this, here we have the anomeric carbon of 1, but notice this is now an acetal because we have a carbon with OR, OR. There's no OH. There's two alkoxy groups. So that is now an acetal linkage. And that linkage can occur when the glucose is in an alpha position at the anomeric carbon or a beta position. And that makes two different polysaccharides, cellulose and starch. They're both polysaccharides, glucose in long chains. The only difference is alpha or beta connectivity at the anomeric carbon.